A warm welcome. This is Electric Energy Generation Utilization and Conservation course with lecture 1.1 focusing on lighting and laws of illumination. Lighting. Lighting is a natural phenomenon which is very vital for the existence of any living being. Humans depend on light for all activities. Life involves day-night cycles beginning with the sunrise and ending with sunset. Prehistoric man had activities limited only to daytime, and the artificial light enables the extended activity period employing in a planned, optimized manner, thereby minimizing the resources. Vision is the most important sense, accounting for 80% of information acquisition for humans. Though the information may be acquired from sun or moonlight, it can also be obtained from the artificial light, which is nearer to the natural lighting. Time Muller's definition for lighting says, we say the lighting is good when our eyes are clearly and pleasantly perceiving the things around us. Therefore, artificial light should be functional and pleasant, both physiological as well as psychological. This is often achieved by employing multiple sources, because we know with a single source the brightness of the lighting may be less when compared to that of multiple sources. If more than one sources, and this multiplication of any source has to be considered optimally based upon the requirement. And also it must be borne in mind that the sources should be economic and energy efficient. So electrical energy, the base which is providing the artificial lighting in today's world, can be of AC type or DC type. AC is nothing but alternating and DC is nothing but the direct current type. Usually electric power supply is AC in nature, either single phase or three phase in India. So these are some of the properties of the lightings. The four main properties are incandescence, luminescence, fluorescence and phosphorescence. While considering incandescence, thermoluminescence is by definition the radiation at the highest intensity. The sources employing this process are the incandescent lamp, gas lamp, flames, wax candles, etc. They lead to a continuous spectrum of radiation, but the heating will be very much greater in this case. Next, let us consider luminescence, which by definition is a chemical or electrical action on gases or vapor radiation. Here, the color of the radiation can be made different by employing a different material. Usually, this process leads to line or band spectrum. While considering fluorescence, it is a process in which the radiation is absorbed at one wavelength and is re-radiated at another wavelength. This re-radiation makes the light radiation more visible. For example, if we have UV impinging on uranium fluorescent oils, we can observe the fluorescence effect. Next, while considering the phosphorescence, it is a process when energy is absorbed at some time and radiated later as a glow. Examples of this process are luminous paints that contain calcium sulfide that lead to phosphorescence. They produce light radiation even after exposure. They produce light radiation only after the exposure to the light. In practice, the efficient lighting can be obtained from luminescence and fluorescence. The fluorescent lamp is luminescent source of low luminous value, activating the fluorescent surfaces which lead to visible radiation. Here actually the intensity depends upon the gas or the vapor involved and the phosphor material. However, the temperature has to be considered because it plays a main role in radiation. So considering all these properties of light, let us move towards the law of illumination. So now we have seen about the lighting as well as its properties. Now let us say how the light has to be illuminated. There are three laws which are focusing upon the illumination level. The first one is law of inverse squares. So what we are going to emphasize is the illumination is inversely proportional to the square of the distance between the source and the object. we are considering two different objects which are parallel. One is A1 with area A1 and the other one with area A2 at a distance of R1 and R2 respectively from the source point of the light. Let us consider the light here. This is the first object and this is the second object. Now we are going to light this source and we are going to find out how the illumination level is present over here as well as here. The luminous flux radiated per steradians, it can be given as I is equal to F divided by omega. That is the total flux. F is nothing but the total flux divided by omega value will give the luminous flux radiated per steradians. So the total luminous flux is nothing but F is equal to I omega. Let us consider the illumination level. Illumination level on any surface area can be given by the total luminescence flux divided by the particular area where it is illuminated. So E1 is equal to F1 by A1. We know F1 is equal to I omega and A1 is equal to omega into R1 square. This is the area. So now after cancelling out the omega value, we get I by R1 square. Next, while you are considering the illumination on the surface area A2, E2 is similar to that of A1, we will get I by R2 square. Now we can prove that we have proved that the illumination level is inversely proportional to the distance of the object from the light source, that is the square value of the distance between the light and the object. This is law of inverse. Here we have I cos theta by d square. So we are considering this is d and this is the value h. That is, it is a normal line to the source. So while you are considering the normal line, it becomes the d square value becomes h by cos theta, because cos theta is equal to h by d, and therefore h by cos theta will give you the d value, its square term. So obviously it becomes I cos cube theta divided by h square. So while you are considering the normal point, the law states that the illumination level is directly proportional to the cosine cube value. And here we can see that d is the distance between the source and the surface in meter. We have already seen h is the height of the source from the surface, and capital I is the luminous intensity in candela. Thus the cosine cube law states that the illumination at any point on a surface depends upon the cube of cosine of the angle between the line of flux and the normal at that point.